Hello everybody, welcome into another lesson. So today we are going to solve single angle trigonometric equations. In the next lesson we'll do multiple angle trigonometric equations, but in this lesson we're going to solve single angle trigonometric equations, and we're going to split this into different parts. There's different styles of these. What do I mean by single angle? So in your function, your trig function, you just have a 1x or a 1 theta. It's just simply that time, it's just that x or that theta, whatever variable you choose, times 1. And as you see, I drew some 45, 45, 90 right triangles and 30, 60, 90 right triangles, and I would encourage you to do the same when you go to solve these, because you'll have those ready to reference. So, okay, we have 2 times the cosine of x plus 1 equals 0. Well, the idea is, like any algebra equation, though it's trig, you kind of start out the same way. You want to get the variable term by itself. So this would turn into 2 times the cosine of x equals -1. And then the cosine of x would equal -1/2. Now, when you're trying to find the general solution, because you may be asked to find equations from the interval from 0 to 2 pi, or you may be asked to find the general solution. Well, to find the general solution, you're still going to start out solving from 0 to 2 pi, but there's something else we do at the end. But what I also want to mention is that you can take the inverse cosine, but keep in mind that the inverse cosine for a negative would only give you in the second quadrant. If you're going to find the general solutions, you're also going to need a third quadrant answer, because the cosine's negative in the third quadrant. So that's why you probably don't want to just rely on the inverse cosine. It's probably better in general to ask the cosine of what angle gives me -1/2. Well, that's definitely going to be a 30 and 60, 90. That's based off of a 60-degree reference angle would give me cosine of 60's 1/2, but in the second quadrant, that would be 2 pi over 3. And then, what else are we going to have? In the third quadrant, you would get 4 pi over 3. Because you always want to go from 0 to 2 pi when trying to find the general solutions, or even if it's just restricted to 0 to 2 pi. Now, unlike just solving from 0 to 2 pi, the general solution means infinitely many solutions in theory. But there's an easy way to express it. Yeah, we're not going to sit here and write out every single solution till kingdom come, because we'd still never be done doing it. But you have x equals 2 pi over 3 and 4 pi over 3. But what is the period of the cosine function? It's 2 pi, right? So how you're going to denote that is plus 2n pi. That n stands for an integer, so that's going to be integer multiples of 2 pi. And then you're going to do the exact same thing for the 4 pi plus 3 for the general solution. So you have two solutions here of x equals 2 pi over 3 plus 2n pi, and then 4 pi over 3 plus 2n pi. That accounts for the infinite nature of the solutions. And I got more of these. And right now we're just doing, to start with, we're doing linear trigonometric functions of one function. Alright. How about the square root of 2 times the sine of x plus 1 equals 0. So we have the square root of 2 times the sine of x plus 1 equals 0. Well, get that sine of x term by itself, so this would turn into the square root of 2 times the sine of x equals -1. And then this would give you that the sine of x equals -1 over the square root of 2. In fact, don't worry about rationalizing your denominator this time. It's pretty irrelevant to what we're trying to do. So the sine of x equals -1 over the square root of 2. So in the interval from 0 to 2 pi, where is the sine negative? In the third and fourth quadrants, right? So let's see. If we take the sine of 45, you get 1 over the square root of 2, but that's going to be a 45-degree reference angle. In the third quadrant, if you add 45 to 180, which would be pi over 4 to pi, you would get x equals 5 pi over 4. So x would equal 5 pi over 4 plus a 2n pi. And then you would also have it in the fourth quadrant, which would end up being 7 pi over 4 plus 2n pi. So those would be your two solutions. You would get that x equals 5 pi over 4 plus 2n pi, 7 pi over 4 plus 2n pi. Alright, let's see. Square root of 3 times the secant of x. Whoops, I didn't want to do that yet. Minus 2 equals 0. Of course, I gotta drop the eraser like I do every lesson. Okay. So the square root of 3 times the secant of x minus 2 equals 0. Well, let's get that secant term by itself. So this would turn into the square root of 3 times the secant of x equals positive 2, which would mean the secant of x equals 2 over the square root of 3. Alright, so this is a positive secant, so this is going to occur in the first and fourth quadrants. So where does the secant of what angle gives you 2 over the square root of 3? So secant is hypotenuse over adjacent. That's going to be based off of a 30-degree angle, which in the first quadrant is pi over 6. So you'll get that x equals pi over 6 plus that 2n pi. And then if it occurs again in the fourth quadrant, that would be 11 pi over 6 plus 2n pi. So your two solutions should end up being x equals pi over 6 plus 2n pi and 11 pi over 6 plus 2n pi. Alright, let's see. Cotangent of x plus 1 equals 0. So we're given the cotangent of x plus 1 equals 0. So this would become the cotangent of x equals -1. Okay, well, the cotangent of x equals -1. Where is the cotangent negative? In the second and fourth quadrants is where it's negative. Well, let's look at, to get a cotangent of -1, it looks like the cotangent of 45 degrees would give you +1, So in the second quadrant, take pi over 4 away from pi, you would end up getting initially that x equals 3 pi over 4. And then if you want to find it in the fourth quadrant, take pi over 4 away from 2 pi, you would get 7 pi over 4. But what is the period of the cotangent function? It's just pi. So you could write this as x equals 3 pi over 4 plus n pi, because the period of the cotangent function is only 1 pi, so it would just be integer multiples of pi. And then you might be tempted to write 7 pi over 4 plus n pi, which you wouldn't be wrong, but it's unnecessary. The reason is because let's say I make that n 1, and I just add pi to 3 pi over 4, I'll get 7 pi over 4. So really, you would just be listing the same solution twice. So you could write this as x equals 3 pi over 4 plus n pi. That would suffice. And the nice thing is this works out very nicely for the tangent and cotangent functions, because a perfect pi would pretty much generate the same angle that you've got. It would generate both angles. So there's no need to list the same solution twice. So this would suffice right here. Okay, let's see. We have the tangent of x plus the square root of 3 equals 0. So the tangent of x plus the square root of 3 equals 0. So this would turn into the tangent of x equals negative of the square root of 3. Well, the tangent of what angle gives you negative square root of 3? Well, first of all, where's the tangent negative? That's going to be in the second and fourth quadrants. So if we look at our 30, 60, 90 triangle, a tangent of 60 would give you positive square root of 3, so this is going to be based on a 60-degree reference angle. So in the second quadrant, you would get that x equals 2 pi over 3. And then again, in the fourth quadrant, that would end up being 5 pi over 3. Now, to write the general solution, you'll get that x equals 2 pi over 3, but it's plus n pi, because the period of the tangent function is only 1 pi. And we don't need to account for 5 pi over 3, only for the fact that if I make that n1, which would turn into 2 pi over 3 plus pi, this will also account for 5 pi over 3. So I can just write this as one general solution as x equals 2 pi over 3 plus n pi. Alright. I think we're about done with the single variable, with the single function linear ones. No, I got one more. Got just one more. So we have 2 times the sine of x plus 1 equals 0. Alright. Well, let's get this sine of x term by itself. So this would turn into 2 times the sine of x equals negative 1, which would give you that the sine of x equals negative 1/2. Alright, so where's the sine negative? That's going to be in the third and fourth quadrants. If we look at our 30 and 60, 90 right triangle, the sine of 30 gives you 1/2, so this will be based on a 30-degree reference angle or a pi over 6 reference angle. If we want to go to the third quadrant, add pi over 6 to pi, you would get that x equals 7 pi over 6, and then in the fourth quadrant, that would be 11 pi over 6. So you have to write two general solutions. X would equal 7 pi over 6 plus 2n pi because the period of the sine function is 2 pi. And then you'll also have 11 pi over 6 plus that 2n pi. So your two general solutions are x equals 7 pi over 6 plus 2n pi and 11 pi over 6 plus 2n pi. Alright, so that's it for the single trig function linear. We're going to slowly transition into higher power ones for today. So let's start out with an already, it's sort of quadratic, but we're going to do it already in factored form. So you have a factored trig function. You have the cosine of x times the cosine of x minus 1 equals 0. Well, up until now we have not had to check for extraneous solutions, but since we're getting into, in theory, this is a quadratic, we need to start checking for extraneous solutions. Well, you're going to treat this like you would any other algebra function. You're going to set each of these factors equal to 0. So if you set the cosine of x equal to 0, when is the cosine 0? Well, that's going to be pi over 2 as well as 3 pi over 2. It's okay to initially write out what the solutions are in the interval from 0 to 2 pi, but we'll refine it once we determine any extraneous solutions and all that. Alright. Now how about when the cosine of x minus 1 equals 0, that would just give you the cosine of x equals 1. In the interval from 0 to 2 pi, when does the cosine of x equal 1? That only occurs at 0. When x equals 0. So we need to see if any of these are extraneous solutions. So put in x equals 0 first. You would get 1 times 0. We know the 0 checks out. And then you're going to have, if we put in pi over 2, you would get 0 times negative 1, which is 0. So pi over 2 checks out. If you put in 3 pi over 2, you would get 0 times negative 1, which is also 0. So all three of these solutions check out. So how are we going to write this? Well, okay, so keep in mind something here. We could, in theory, write 0 plus 2n pi. But anything plus 0 is itself, right? So we can definitely just write 2n pi. So that would account for any integer multiples of 2 pi, whether that's 0, negative 1, positive 1, what have you, you'll get the same thing. Now, what about how do we write pi over 2 and 3 pi over 2? Now, of course, the period of the cosine function is 2 pi. However, if I take pi over 2 and I add pi to it, I get 3 pi over 2. So there's an easier way to do this. You can also write pi over 2 plus n pi. Yes, it's true that the period is 2 pi, but pi over 2 plus pi will give you that 3 pi over 2. Whenever you have the angles that are on the axis themselves, sometimes it's easier just to write it this way because this will also account for the 3 pi over 2. So really all you need to do is list two general solutions. You'll get that x equals 2n pi and then pi over 2 plus n pi. Do we have any other factored forms that are already factored? I want to determine that. Nope, that was it for the already factored. Let's get into some quadratic. Alright, so we have 3 times the cosecant squared of x minus 4 equals 0. So this is a quadratic trig function. Well, it might be easiest to move the 4 over to the right-hand side. So this would give you 3 times the cosecant squared of x equals 4. So then you would get cosecant squared of x equals 4 over 3. Now we just take the square root of both sides, but it's going to be the positive and negative of the right-hand side. This would end up being the cosecant of x equals both plus and minus 2 over the square root of 3. Alright, so this is anywhere in the interval from 0 to 2 pi where you have a cosecant of 2 pi over 3, whether it's positive or negative. So let's see where the cosecant in general is 2 over the square root of 3. That's going to be a 30-degree angle, so all these are going to be based off of a pi over 6 reference angle. So you can start out with x equals pi over 6. In the second quadrant, that would be 5 pi over 6. In the third quadrant, that's 7 pi over 6. In the fourth quadrant, that's 11 pi over 6. But we're not done yet. You have to check for extraneous solutions since this is a quadratic. So we're going to test each single one of these. Think of this more as a checklist. So 3 times the cosecant squared of pi over 6 minus 4 should equal 0. Okay, so that would be 3 times, what is the cosecant of pi over 6? That's 2 over the square root of 3. That would be that quantity squared minus 4 equal to 0. So that would give you 3 times 4/3 minus 4 would equal 0, which would just give you 4 minus 4 equals 0. So yes, that checks out. And in fact, all these are going to check out because even if you have a negative 2 over the square root of 3, once you square it, it'll become positive. You'll end up with the same thing. So every last one of these check out. Now, it might look like you have to write 4 general solutions. So let's start with the general solution. Start with pi over 6. The period of the cosecant, that's also 2 pi. So that's going to equal pi over 6. And you would think plus 2n pi, but here's the thing. If I add pi to pi over 6, what will I get? I would end up getting 7 pi over 6. So I can literally write pi over 6 plus n pi. That would give me the full solution to this equation because that pi over 6 plus another pi would also account for 7 pi over 6. And then I could use my 5 pi over 6. And if I add 1 pi to that, I'll end up getting 11 pi over 6. So I can also write 5 pi over 6 plus n pi. That would be the 2 general solutions, which would really account for all 4 of these in the interval from 0 to 2 pi. So you only have to write 2 general solutions. X would equal pi over 6 plus n pi, and 5 pi over 6 plus n pi. we have 3 times the cotangent squared of x minus 1 equals 0. So 3 times the cotangent squared of x minus 1 equals 0. So this is going to become 3 times the cotangent squared of x equals positive 1. So the cotangent squared of x would equal 1/3. Then take the square roots, you'll end up getting the cotangent of x equals both plus and minus 1 over the square root of 3. Okay, well, this is going to be based on where the cotangent equals either positive or negative square root of 1 over the square root of 3. If we look at our 30, 60, 90 right triangle, this would end up being based on a 60-degree angle. The cotangent of 60 is 1 over the square root of 3, which would otherwise known as pi over 3. Since we're considering both roots, we can list x equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. That's going to be every pi over 3 in the interval from 0 to 2 pi. But again, think of this more as a checklist. Let's test these to make sure these are not extraneous roots. So if I take 3 times the cotangent squared of pi over 3 minus 1, I should get 0. So 3 times, what is the cotangent of pi over 3? That's going to be 1 over the square root of 3, but that's squared. Minus 1 equals 0. So that would be 3 times 1/3 minus 1 equals 0. Well, that would end up giving you 1 minus 1 equals 0. So yes, the pi over 3 checks out. In fact, as a matter of fact, whether you put in positive or negative values, since you're squaring it, it's still going to check out in the original. So all of these check out. Now, again, it might look like we have to write 4 general solutions, but we don't. So x equals pi over 3, start with that. Now, what's the period of cotangent? It's just 1 pi. So pi over 3 plus that n pi. If you add pi to pi over 3, that accounts for the 4 pi over 3. So you're good for both of those. Then use your 2 pi over 3. And then if I add n pi to that, that'll also account for 5 pi over 3. So the 2 general solutions would be x equals pi over 3 plus n pi, and then 2 pi over 3 plus n pi. Alright, let's see. 4 cosine squared of x minus 1 equals 0. So 4 cosine squared of x minus 1 equals 0. Well, this would turn into 4 cosine squared of x equals positive 1, which would give you the cosine squared of x equals 1/4. Then we take our square roots, you'll get the cosine of x equals both plus and minus 1/2. So we got both roots, negative and positive. So we're going to consider everywhere where the cosine is 1/2 in the interval from 0 to 2 pi. So if we look here, the cosine of 60 is 1 over 2, which is a pi over 3 angle. So x would equal pi over 3, and then again you'll have it, because you have both roots, this will occur in every quadrant. You would have 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, well, we can already tell, and based on our experience with these past few examples, no matter which of these we put in, you're going to square, whether it's positive or negative, you'll end up getting the left side equals the right. So all these are going to check out. So how are we going to write the general solutions? It might look like we have 4 general solutions because the period of cosine is 2 pi. But let's start with pi over 3. Now, you would think to write next to that would be plus 2n pi. But if you write just plus n pi, you'll account for that 4 pi over 3. So you can actually write pi over 3 plus n pi, and then take your 2 pi over 3, and you can do the same with that. Plus n pi, that would also account for 5 pi over 3. So your solutions are going to be x equals pi over 3 plus n pi, and then 2 pi over 3 plus n pi. That would account for all 4 of these in the interval from 0 to 360, and then from to infinity and beyond. All right. Good one. So 3 tangent squared of x minus 1 times, let's see, tangent squared of x minus 3 equals 0. So you have double quadratic factors. Well, again, you're going to set each of these equal to 0. So start with that 3 tangent squared of x minus 1. Set that equal to 0. So you would get 3 tangent squared of x equals 1, which would give you the tangent squared of x equals 1/3. Take your both positive and negative square roots, you would get the tangent of x equals plus and minus 1 over the square root of 3. So, okay, we have to consider the both positive and negative roots here. So where does, for a reference angle, where does the tangent equal 1 over the square root of 3? That would be for a 30-degree angle, which would be pi over 6. And we're considering both roots, so x would equal pi over 6. Then every quadrant, that would be 5 pi over 6, 7 pi over 6, and then again at 11 pi over 6. All right. And these are all going to be on a checklist. But before we try to put these in, let's solve for the other factor. So let's take that tangent squared of x minus 3, set that equal to 0. You would get the tangent squared of x equals 3. So the tangent of x would equal both plus and minus the square root of 3. So we got all quadrants again because you have both positive and negative roots. Where do you, for what reference angle do you get a tangent of the square root of 3? Well, this time it's going to be 60. So that would be a pi over 3 reference angle. So pi over 3, and in every quadrant then you'll have 2 pi over 3. Then you'll end up having 4 pi over 3, and then you'll have it again at 5 pi over 3. So we have 8 angles, it looks like, that would work to solve this. Well, let's check out our first angle, pi over 6. Well, the tangent of pi over 6 is 1 over the square root of 3. You square that, you get 1/3. 3 times 1/3 is 1, minus 1 is 0. All you need is this to equal 0. You don't really care what that equals. If this equals 0, the whole thing equals 0. As the matter of fact, every multiple of pi over 6 is going to check out in this case. Now let's deal with the multiples of pi over 3, which would be dealing with this factor here. The tangent of pi over 3 is the square root of 3, so you square that, you get 3 minus 3, which is 0. It doesn't matter what this would equal. In fact, this would work for every multiple of pi over 3. So it almost looks like we have 8 general solutions, but we really can write this in half of that. Let's start with our pi over 6. Alright, so pi over 6, and then the period of the tangent function is pi. So if we write pi over 6 plus n pi, well, that would account for 7 pi over 6 also. And then if we write 5 pi over 6 plus n pi, that's also going to account for 11 pi over 6. So we've accounted for the pi over 6's. Then if we take that pi over 3 plus n pi, that would also account for the 4 pi over 3. And then if we wrote 2 pi over 3 plus n pi, that would also account for 5 pi over 3. So here are your 4 general solutions. X equals pi over 6 plus n pi, 5 pi over 6 plus n pi, pi over 3 plus n pi, and then 2 pi over 3 plus n pi. All right. I have 2 more simple quadratics. 2 more simples, then we got some others. Alright, so the cosecant squared of x minus 2 equals 0. Cosecant squared of x minus 2 equals 0. This would turn into the cosecant squared of x equals 2. So that means the cosecant of x would equal both plus and minus the square root of 2. So where does the cosecant of x for a reference angle equal the square root of 2? That would be a 45-degree angle, which would be a pi over 4 reference angle. So in the interval from 0 to 2 pi, you would start with pi over 4, and since you have both positive and negative roots, you'd have 3 pi over 4. And then you would also have 5 pi over 4 and 7 pi over 4. And it looks like we have 4 general solutions, but really you only have one that will account for all 4 of them. So x is going to start with equaling pi over 4. Now here's the thing. Yes, it's true the period of the cosecant is 2 pi. But if I add pi to this, I'll get 5 pi over 4. But another factor to this, we're also accounting for both roots. The only angle you can add pi over 2 and land exactly where you need to in the next quadrant is a pi over 4 angle. If I actually did pi over 4 plus n times pi over 2, if I did integer multiples of pi over 2, I would get 3 pi over 4, 5 pi over 4, and 7 pi over 4. So I can actually write this as one general solution. X would equal pi over 4 plus n pi over 2. That would account for every single pi over 4 multiple from here to kingdom come. Alright. Tangent squared of x minus 1 equals 0. So this would turn into the tangent squared of x equals 1. So the tangent of x would equal both plus and minus 1. So what reference angle gives you a tangent of 1? That would be a 45-degree angle, which is pi over 4. So x would equal pi over 4. But we have positive and negative roots, so this would be every pi over 4 multiple. So then you'd have 3 pi over 4, 5 pi over 4, and then 7 pi over 4. Well, it looks like we have 4 general solutions, or it looks like we have 2 because the period of tangent is pi, but we can write all this as 1. Because we are considering both positive and negative roots, we start with that pi over 4, and then if we add pi over 2 to pi over 4, we'll get 3 pi over 4, and we can keep adding that pi over 2 and get 5 pi over 4, 7 pi over 4, and so on. So really, we can write one general solution of x equals pi over 4 plus n pi over 2, and that'll account for every multiple of pi over 4. Okay, so those are the simple quadratics. Let's do trig equations of more than one function. So let's say we have the sine squared of x equals 3 times the cosine squared of x. So all of the sudden, we have this. We have more than one function. This is really where the business of extraneous solutions is going to come into play. So I'm going to arrange I'm going to switch these sides around. There's a reason for that. So 3 times the cosine squared of x equals the sine squared of x. Now, take your pick. You can use either Pythagorean identity. You can try to get this down to a sine or just a cosine. As for me, what I'm trying to do is make that sine squared into terms of cosine squared. So this would turn into 3 cosine squared of x equals 1 minus the cosine squared of x. You can use your Pythagorean identities. Alright. Well, you could have also gone with the cosine squared equals 1 minus sine squared, but do you want to have that extra multiple of pi over 3? Not pi over 3, the extra multiple of 3. I don't think you do. So this is a lot easier. Now let's get the right-hand side equal to just 1. That would end up becoming 4 times the cosine squared of x equals positive 1. So the cosine squared of x is equal to 1/4, which would turn into the cosine of x equals both plus and minus 1/2. Alright, so we are considering both roots again. Where does the cosine of x for a reference angle equal 1/2? The cosine for that reference angle is going to be at 60, right? So that would be pi over 3. And since we're considering both positive and negative roots, so you would get x equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now this is where we have to pay particular attention. We have to see, you have to take each of these, stick these into the original unfactored, unchanged equation to see if the left side equals the right. And if it doesn't, you have an extraneous solution. So let's put in pi over 3. If you take the sine squared of pi over 3, what's that going to equal? That would equal 3 times the cosine squared of pi over 3. Well, is this true? What is the sine of pi over 3, which is 60? That would be the square root of 3 over 2. So you would take that square root of 3 over 2 raised to the second power, set it equal to 3 times what's the cosine of pi over 3? That's 1/2 raised to the second power. Square this side, you would end up getting 3/4 is equal to 3 times 1/4, which we know is true. 3/4 equals 3/4. In fact, all of these multiples would work because whether it's positive or negative, you're squaring it, which will turn it positive. So all these actually hold up in this case. Now, yes, it's true the period of sine, both sine and cosine, is 2 pi. But if we write x equals pi over 3 plus n pi, you'll actually account for the 4 pi over 3. And then if you take that 2 pi over 3 plus n pi, you'll also account for the 5 pi over 3. So your two general solutions are x equals pi over 3 plus n pi and 2 pi over 3 plus n pi. All right, what do we got here? Well, this is still the same function, but it's a higher power than 2. We have 3 times the tangent cubed of x equals the tangent of x. So let's get this all to one side. This would turn into 3 times the tangent cubed of x minus the tangent of x is equal to 0. We can definitely factor out a tangent of x, so you'll end up getting the tangent of x times 3 times the tangent squared of x minus 1 equals 0. Now you just got to take each of these factors and set them equal to 0. So the tangent of x equals 0. Where does the tangent in the interval from 0 to 2 pi equal 0? Well, that would be x equals both 0 and pi. And then what about that 3 tangent squared of x minus 1 equal to 0? So this would turn into 3 times the tangent squared of x equals 1. So the tangent squared of x equals 1/3. So the tangent of x is going to equal both plus and minus 1 over the square root of 3. Now we're considering every angle. We are considering every possible angle because we have both positive and negative roots. So for what reference angle does the tangent equal 1 over the square root of 3? That'd be a 30-degree angle, which would be pi over 6. So you would have x equals pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 in the interval from 0 to 2 pi. But let's start verifying all of these angles and see if we have any extraneous solutions. If I take 3 times the tangent cubed of 0, would that equal the tangent of 0? Well, that would literally be 3 times 0 equals 0, so yes, it would. And you would get the same thing with pi. So both 0 and pi actually hold up there. That'll hold up just fine. Now, what about your pi over 6 multiples? So let's take 3 times the tangent cubed of pi over 6. Would that equal the tangent of pi over 6? That's what we have to determine. Well, okay, so this would be 3 times... What is the tangent of pi over 6? That's 1 over the square root of 3. So this would be 1 over the square root of 3 cubed, would then equal 1 over the square root of 3. Alright, well, so how about then that 1 over square root of 3 cubed? That'd be 3 times 1 over 3 times the square root of 3 would equal 1 over the square root of 3, which actually you would get the left side equals the right. 1 over the square root of 3 equals 1 over the square root of 3. So this actually checks out. In fact, it would for every multiple of pi over 6, because you cube a negative, you'll also get a negative, and it would work for every multiple of pi over 6. So it looks like we have 6 general solutions. And in theory we do, but we can write it as less than that. So this 0 and pi, well, the period of tangent is pi, so you could literally just write n pi. That would also account for 0, pi, and every other pi from here to kingdom come. Now, your multiples of pi over 6, you could do pi over 6, and then your period of tangent is pi, so pi over 6 plus n pi would account for that 7 pi over 6. And then the 5 pi over 6 plus n pi would also account for that 11 pi over 6. So you can actually write this as 3 general solutions. X equals n pi, pi over 6 plus n pi, 5 pi over 6 plus n pi. All right. How many more do I got? 4, 5, 6, 7, 8, 9. All right, don't kill me, but I got about 9 more, but these are all very, very important. All right, so we have 2 sine squared of x is equal to 2 plus the cosine of x. 2 sine squared of x equals 2 plus the cosine of x. Well, your sine is squared, your cosine's linear. I'm definitely going to suggest we convert that sine squared into terms of cosine. So this would be the same as 2 times 1 minus the cosine squared of x equals 2 plus the cosine of x. So this is going to turn into 2 minus 2 times the cosine squared of x. I don't know why I put a parenthesis there. Would equal 2 plus the cosine of x. What would just equal, cosine of x. Okay. We try to get everything to one side now. This would turn into 2 cosine squared of x plus the cosine of x equals 0. So this ended up actually not being so bad. You can definitely factor out a common cosine of x, right? So you would get the cosine of x times 2 cosine of x plus 1 is equal to 0. Well, okay, set each of these factors equal to 0. You would get the cosine of x equals 0. And where does that cosine equal 0? In the interval from 0 to 2 pi. That'd be x equals pi over 2 and 3 pi over 2. That's just for your checklist to start with. Now then you can deal with 2 times the cosine of x plus 1 equals 0, which would give you 2 times the cosine of x equals negative 1. So then you would get the cosine of x equals negative 1/2. Now we have to consider only where the cosine is negative 1/2. That would be in the second and third quadrants. This is going to be based off a 60-degree reference angle or a pi over 3 reference angle. So in the second quadrant, that would be 2 pi over 3. In the third quadrant, that would be 4 pi over 3. All right. Now it's time to check for extraneous solutions. If I take pi over 2, well, I can tell you right now both of these are going to work because the sine of pi over 2 is 1. Well, 1 squared is 1. 2 times 1 equals 2 plus 0. That's going to work. And even 3 pi over 2 would work, though the sine of 3 pi over 2 is negative 1. If you square that, you'll get a positive 1 times 2 is 2. That would equal 2 plus 0. So yes, your 3 pi over 2 also works. Now where it gets interesting here is going to be this 2 pi over 3 and 4 pi over 3. So let's see if these work in the original equation. So 2 times the sine of 2 pi over 3 squared, would that equal 2 plus the cosine of pi over 3? Well, okay, what is the sine of 2 pi over 3? So what's the sine of 60? That would be the square root of 3 over 2. So this would be 2 times the square root of 3 all over 2 squared. Would that equal 2 plus that cosine of pi over 3, which is actually 2 pi over 3, 2 plus that negative 1/2. This is about to get very interesting. Well, 2 times, so this would turn into 2 times 3/4. That would equal 2 minus 1/2. 2 times 3/4, that's 3/2. That would also equal 3/2. So we know that 2 pi over 3 checks out. And if you put in 4 pi over 3, it would actually also check out. So every solution here actually checks out this time. But it's always good to verify for extraneous roots. Okay. So let's deal with this pi over 2 and 3 pi over 2 business. Well, pi over 2, if you add pi to that, you'll get 3 pi over 2. So you can say x equals pi over 2 plus n pi over 2. So that'll work. And then you have 2 pi over 3 plus 2n pi, because the period of sine and cosine is 2 pi, and then you'll end up also having 4 pi over 3 plus 2n pi. So these would be your three general solutions: pi over 2 plus n pi over 2, 2 pi over 3 plus 2n pi, and 4 pi over 3 plus 2n pi. I don't think we're going to go the full 8 more. I don't see a reason for that. I do have a couple good ones, though. I do have 3 more good ones. Why don't we do this? So we're going to have the secant of x, cosecant of x, is equal to 2 cosecant of x. This just thickened a lot. I think it's safe to say we're definitely going to want to use some reciprocal identities. So the secant is known as what? That's 1 over the cosine of x. This would be times 1 over sine of x. Would end up equaling 2 over the sine of x. Well, what you're going to be left with then is that 2 sine of x, 2 over sine of x, is equal to 1 over the cosine of x sine of x. So what's about to happen here? We want to get this right side equal to 0, so this would be 2 over the sine of x minus 1 over the cosine of x sine of x is equal to 0. Well, I think it's safe to say we definitely want to get a common denominator, right? The common denominator would be cosine of x sine of x, so all we have to do is multiply the first term by cosine of x. You would end up getting 2 cosine of x minus 1 all over cosine of x sine of x equals 0. Now, notice we have a denominator. That means we already need to check for extraneous roots in our denominator wherever the cosine or sine equals 0. Well, in this case, it's going to be at any of the multiples of pi over 2 would produce a 0 in the denominator, right? So we already know that x cannot equal integer multiples of pi over 2, whether 0, pi over 2 pi, 3 pi over 2, or 2 pi. Any of those will give you a denominator of 0. So if we get any multiples of pi over 2, we got to exclude those. But if you multiply both sides by the denominator, you're left with a simple equation now of 2 times the cosine of x minus 1 equals 0, which would end up giving you 2 times the cosine of x equals 1. So the cosine of x would equal 1/2. Now we're only concerned with where the cosine is positive. The cosine is positive in the first and fourth quadrants. So the cosine of 60 gives you 1/2. So that would mean that x equals pi over 3, and then again at 5 pi over 3 for the fourth quadrant. Well, so far we don't have to exclude them because they're not multiples of n pi over 2, but we still have to check to make sure these stack up in the original equation. So take that secant of 5 pi over 3 times the cosecant of pi over 3. Set that equal to 2 times the cosecant of 5 pi over 3, or pi over 3, excuse me. Alright, so what's the secant of pi over 3, which is 60. Secant is hypotenuse over adjacent. That would be 2. So this would give you 2 times, what's the cosecant of pi over 3? That's opposite over, that's hypotenuse over opposite. So that'd be 2 over the square root of 3, which would end up giving you 2 times 2 over the square root of 3. So very good. Pi over 3 checks out. And even 5 pi over 3 would, because you would have a negative of this on the left side equaling a negative of that on the right side. So both of those solutions actually check out. So I think we're only going to do 2 more after this. So x would equal pi over 3 plus 2n pi, because the period of the secant and cosecant both are 2 pi. And then you'd also have 5 pi over 3 plus 2n pi. So both of our actual solutions checked out very nicely. 2 more. I'm going to do them in this style, because I think we get the quadratics pretty well. All right. Good one. 2 times the sine of x plus the cosecant of x equals 0. So we have 2 times the sine of x plus the cosecant of x equals 0. Well, I think it's safe to say we definitely want to use a reciprocal identity with the cosecant of x. So 2 times the sine of x plus 1 over the sine of x would equal 0. Well, we already have an extraneous solution. That's going to be where you have a denominator of 0. Where does the sine of x equal 0? That would be integer multiples of pi, such as 0, pi, 2 pi, so on. So x cannot equal integer multiples of pi. We have to exclude those from the solutions if we get them. Okay, so you want to get a common denominator, which would be sine of x. So this would end up becoming 2 sine squared of x plus 1 all over the sine of x equals 0. Multiply both sides by sine of x, you'll get 2 sine squared of x plus 1 equals 0, which would end up giving you 2 sine squared of x equals negative 1, which would give you the sine squared of x equals negative 1/2. Well, what do you know? You would be taking the square root of a negative number, which, dealing with trigonometric values of imaginary numbers is way more abstract above the stuff that's even I'm familiar with, that I'm not even completely familiar with. So we're only concerned with the set of real numbers. In this case, you have no solution. I should say no real solution. That's the best way to put it. So there is no real solution to this equation in this case. And you will sometimes have that. I want to do one more similar to this, then we'll be done with the lesson. Good one. 3 functions. So we have the cosine of x plus the sine of x tangent of x equals 2. So we have the cosine of x plus sine of x tangent of x equals 2. Well, I think it's safe to say we want to convert that tangent into a reciprocal identity. So this would become the cosine of x plus, let's put a parenthesis here, the sine of x times the sine of x over the cosine of x equals 2, which will simplify into the cosine of x plus the sine squared of x over the cosine of x is equal to 2. Well, already we have to be concerned with an extraneous solution. So that's going to be when that cosine of x equals 0. Where does the cosine equal 0? That's going to be at integer multiples of pi over 2. No, that would be at odd multiples of pi over 2. So, well, x cannot equal pi over 2 plus n pi. It can't equal any integer multiple of pi plus pi over 2, because the cosine at pi over 2 or 3 pi over 2 is 0. So it would be undefined there. Now we obviously need to get a common denominator on the left-hand side. So that's going to end up being the cosine squared of x plus the sine squared of x all over the cosine of x is equal to 2. Okay, so if you multiply both sides by the cosine, you'll end up getting cosine squared of x plus sine squared of x equals 2 cosine of x. Well, what's the left side? That just turns into 1, doesn't it? So this would become 2 times the cosine of x equals 1. So that would end up giving you the cosine of x equals 1/2. Since we have a positive 1/2 for the cosine, where's the cosine positive? In the first and fourth quadrants. So the cosine of 60 is 1/2. So this will be a 60-degree reference angle. That's going to initially give you that x equals pi over 3 and 5 pi over 3. But we do have to check for extraneous solutions here. Put these into the original equation. So this would be saying the cosine of pi over 3 plus the sine of pi over 3 times the tangent of pi over 3 equals 2. Let's see if that's true. What is the cosine of pi over 3? Well, that's going to be 1/2 plus, what's that sine of pi over 3? That's the square root of 3 over 2 times the tangent of pi over 3, that's the square root of 3 over 1, or simply the square root of 3. Does that equal 2? Well, this would turn into 1/2 plus, 3 over 2, which would be 4 over 2 equals 2. Pi over 3 checks out. However, the question is, Will 5 pi over 3 check out? I'm curious about that. We have to determine that. So what is the cosine? Let's see. Let's do the 5 pi over 3. Checking for extraneous solutions. Alright, so this is going to be a pi over 3 angle in the fourth quadrant. That's still positive 1/2 for the cosine. Plus, okay, the sine of 60, but in the fourth quadrant, that would end up being negative of the square root of 3 over 2. Whoops, not. Then what's the tangent of 60 in the fourth quadrant? That would end up being negative of the square root of 3. Would that equal 2? Well, this would end up giving you 1/2. Negative times negative is positive, so that'd be plus 3/2. Well, 1/2 plus 3/2 does equal 2, so yes, both of these solutions actually check out. Okay, so the general solutions, since the period, well, yes, it's true that the period of tangent is pi, but when in doubt, I would write 2 pi, especially if you only have two solutions that are far apart, like in the first and fourth quadrant. So you would say that x equals pi over 3 plus 2n pi, and then 5 pi over 3 plus 2n pi. So therein lies your general solutions. X would equal pi over 3 plus 2n pi and 5 pi over 3 plus 2n pi. So that's it for this lesson. Next lesson, we're going to solve multiple angle trig equations. So I hope everyone has a great day. Take care.